Bonjour. Thank you all for coming. It is my pleasure to introduce Will Arnuk. Will did his. Do I just need to speak louder? Will did his undergrad at University of Michigan, and then he came to Binghamton University, where we were office mates and lab mates and colleagues under the tutelage of distinguished Professor Tim Lowenstein. Will is defending his PhD at the end of the semester. And then for this series, we've heard a bunch of great talks on how we understand the environment today, our modern environment. And then Will is going to educate us on how we go about understanding the environment in the past, tens of millions of years into the past.
Thank you, Christian, for that nice introduction. As Christian mentioned, I'm going to be chatting with you today about some very ancient sediments. In particular, evaporite minerals, salt minerals that formed in ancient lake basins in Wyoming, Colorado, and Utah. Now that's a bit of, a niche interest of mine, but it has the potential to be really applicable and have some cool implications for those of us that are worried about understanding where future climate is going, how we can mitigate and estimate future climate change, and also, in general, just understand the history of the planet on which we live. So, my first question to sort of guide this discussion today is why the early Eocene? And for those that are not familiar with deep time, geologic time, the early Eocene was about 50 million years ago to maybe about 35 million years ago. So a little bit abstract for us to think that far back in the past. But as it turns out, for those of us that are interested in modeling future climate change, the Eocene is one of the time periods that offers the best perspective for some of these scenarios which we try to understand. So in particular, the IPCC puts out reports every few years on climate change, on what countries are doing to combat climate change, what goals we set for ourselves. And in order to guide those goals, they use a slew of different modeling scenarios, including ones in which governments take aggressive action to combat climate change and ones in which governments take next to no action to combat climate change. So one of those in which the governments take no action, quote unquote, the worst case scenario, by 2100, 2150, those future climates start to look very similar to what we know about Eocene climates. Now, why in particular these basins out west? And let me be clear here, although it shows mapped out ancient lakes in this map on the left side of the screen, these are all dried up now, and they've been dried up for many millions of years. So all that's left is a bunch of dirt and muds and sand and salt. The Green River Basin is an exceptionally well-preserved record. In fact, all of these basins have relatively continuous sedimentation without a ton of holes, gaps in the record, a lot of without any missing information. So we can guide our geochemical analysis to develop a complete and full record at a very high resolution. In particular, we have a bunch of tuffs that come from these basins, and these tuffs are volcanic rocks that are very useful for radiometric dating. So these are interspersed throughout all of the sediments we study. and they're well dated using a bunch of modern updated methodologies. So the age control we have on anything we get out of the Green River Basin is excellent. It's better than marine records in many cases. So if we want to build a good working picture of what this critical time period was in the past, this is the perfect place to develop a really nice record and get analytic measurements and build up a complete story of what that ancient climate was like. So the rocks that are in this basin and the rocks that I particularly focus on are part of two major formations here that are all grouped under the Green River Formation. The first of which occurs in the more northern basin, the greater Green River Basin. It's the Wilkins Peak member. You don't need to know too much about it, but it is a bunch of muds and evaporites, salt minerals. Also in the southern basin in Colorado, there's the Parachute Creek member, which we can think of as the Wilkins Peak's slightly younger sibling in the next basin over. Similar style of sedimentation, pretty good age control, and we can correlate between the basins to fill in any gaps that arise in one or the other. Now, I said these are a bunch of muds and evaporites. This is what they look like. It is meters and meters and meters of green, muddy sediments. In the bottom few, we have a rock called oil shale, which is these laminated brown chunks of core. They're really mudstones, but they have a fair amount of oil kerogen in them. And then on the very bottom, we have a good example of trona, which is one of these evaporite minerals that's pretty interesting to us. So that Wilkins Peak member, again, this small subset of the Green River Formation that has all of these evaporites contained within it. During the time period in which this was deposited, these lakes were highly evaporitic. They were in arid regions. It was hot. They were not getting a whole lot of inflow relative to outflow. So any water that remained in the basin was getting progressively more and more concentrated over time. And we have a bunch of repetitive cycles of mudstone, oil shale, evaporite, mudstone, oil shale, evaporite, and so on and so forth. Which, when we look at it, in a very bird's eye abstract view, it seems very boring. But, these cycles can help us pace our record, and they help us understand the exact timing between the deposition of different beds. So one of the first questions I wanted to tackle with my research stemmed from some of the research my advisor, Tim Lowenstein, had been doing a few years prior, which was, assuming these lake waters, which were pretty unique in how hypersaline they were. Most lakes around the world today are not hypersaline alkaline lakes. What made these so special? Where did their source waters come from? What made them chemically distinct from other basins? And as it turns out, we can glean a lot about what these waters looked like chemically by looking at the evaporite sediments that come out of them. So in this sense, I like to think of these evaporites as time capsules. They offer a really cool picture in terms of remnants of ancient brine and ancient water that we can use to reconstruct what the original chemistry might have looked like. One of the ways we do that is a theory called the principle of chemical divides, which states that depending on whatever your limiting reactant is at a given time, that's going to dictate whether you precipitate one mineral or another. So on the bottom left of this screen, you put a little laser pointer up here. We have a starting brine chemistry with a bunch of different constituents in it: sodium, calcium, potassium, magnesium, chloride, etc. We start concentrating that, and we hit our first chemical divide. If there's more calcium than alkalinity, which is this bicarbonate and carbonate, if there's more calcium than alkalinity, we precipitate away all of the alkalinity, and we're left with a water that has basically just calcium and no alkalinity left. If we continue that process, we then hit another divide with sulfate. So if we have more sulfate than calcium, we precipitate one set of minerals. If we have more calcium than sulfate, we precipitate another. In these basins, we have a pretty unique, both in scale and in style of deposition, set of minerals that precipitates here, these sodium carbonate evaporites. In particular, a mineral called trona and a mineral called nacolite. These are more commonly known as industrial minerals, as soda ash, and they're very, very economically useful to a wide range of industries, to glass making, to auto making. So they have a critical industrial application, but if we see them, we know something about the parent water, which is that there was way more alkalinity than there was calcium. So that's a good starting point. We know two chemical constituents. We also have maybe some hypotheses about where these waters were coming from. And a couple years ago, another collaborator tested out some of these theories by looking at soda springs and looking at sandstones and sediments that line the periphery of these basins. And they found 3 lines of evidence here that point to a source of water coming from the Colorado mineral belt, which is a source of magmatically charged, hyperalkaline hydrothermal waters. The first of which is the sandstones themselves all have flow textures, which point to deposition coming from this region. Deposition flowing from the southeast into the basin here. The second of which is they went and radiometrically dated a bunch of detrital grains. So grains that have been here for a long time that got into the basin in mass and formed a lot of the clastic sandstones. So dating a bunch of those individual sand grains, we can sort of get an idea for what big mountain building events, what big depositional events sourced that sediment. And again, the evidence from the radiometric dating points to a lot of sediment coming from the Colorado mineral belt. Now, the third line of evidence here is they tested some modern spring waters to see could they supply the alkalinity that's necessary to get us these minerals. And they found that it actually doesn't take all that much spring water to get there. So I wanted to take this a little bit further, which is what we did. I threw my computer at the problem in the sense that I set up a bunch of geochemical modeling programs to run thousands of different waters, temperatures, and PCO2s to see if we concentrate the water a little bit, what mineral becomes supersaturated, what mineral has to come out. And then if we keep concentrating that water another step, what mineral has to come out next. And I repeat that process until we're left with not very much water at all. And it turns out that these Colorado mineral belt spring waters do an excellent job of reproducing the same mineral sequences that we see in the cores, in the outcrops of the sediments from this region. So there seems to be a bit of extra evidence here that might point to this Colorado mineral belt's origin of source waters running into the basin, which is that the magmatism that takes place in the Colorado mineral belt has been active throughout the past 50 60 million years in various different pulses. And it's running through the same bedrock and leaching off the same ions before it gets into rivers and then filled in these basins. So we're getting the dregs of whatever the ancient water was, but it still tells us quite a bit about the lake water chemistry, which is a great starting point for tackling future hypotheses. This gave me another interesting piece of information here, which is when I compile all of these geochemical simulations of which minerals come out after concentrating a different water at a different temperature and a different PCO2. And I put them all together and make these three-dimensional plots. Each of these surfaces represents a point in salinity, atmospheric CO2, and temperature space. And as we move up through this plot, we hit a surface, and that tells us that that mineral begins precipitating at that salinity. And if we keep going up, we get another mineral. And if we keep going up, we get a full progression of minerals. But you'll notice these surfaces are relatively flat in salinity space. So without knowing really anything about these ancient basin waters, we're able to figure out if we see one of these minerals in the field, we know what salinity the water was at that given time, which is a pretty cool piece of information if we want to build a record of lake conditions, atmospheric conditions through time. So after some personal communication with our friend and colleague here, Dr. Olson, he noticed a similar progression in a different basin, in different sediments, and pieced together that there is a relation here between these different minerals and sediments and salinity and volume of lake water. So if that's true, we can use whatever we garner here from these salinity records, from these records of evaporite mineral deposition, and turn it into a lake level curve through time. So what I show here is I take that, depositional ranking scheme that we came up with of less saline, less evaporated waters, higher lake level at the very bottom, and at the very top, very highly evaporated, highly saline, very low lake level. And I can apply that throughout hundreds of meters of deposition. So I have a record of hundreds of meters of Wilkins Peak sediments that I've applied this to. And then I can turn that into a salinity curve through time. And similarly, if I know something about the volumes of minerals that were precipitated, which thanks to the industrial applications of Trona, a bunch of companies were highly interested in mapping out how much of each mineral was deposited when. I can pair those with the geochemical modeling and develop a pseudo depth curve through time, which gives us some constraints that this was not an ultra deep basin, maybe 100, 150 meters at most at any given time during evaporite deposition. But we also have to think this was a massively wide basin on the scale of maybe modern Great Lakes. So it was still a very large amount of water. It was just spread out over a great distance. Now that gives me a little beat here to segue into the second project. So we know a little bit about the chemistry of these lake waters through time and the level of the lake through time. But we know next to nothing about the climate, about temperature. So this is where our evaporites once again come to save us here. So in those evaporite minerals, in those salt crystals, there are little tiny pockets of fluid inclusions, of brine that got trapped in the mineral structure and then preserved for millions and millions of years. We can use those to quantitatively study chemistry of the water, but we can also use them to reconstruct temperature because they act like little mini thermometers. So let's talk about the field of paleothermometry in general. If we want to measure the temperature outside, it's pretty easy to do. We can go and take either a classic mechanical thermometer, or we can take a modern thermocouple-based thermometer and go outside and get a reading. If you want to measure the temperature of something millions and millions of years ago, what do? So we have a whole suite of different paleothermometers out there. Most of them are proxies, which is to say that you go and measure some variable that's not itself temperature. But you find in a modern world that there's some correlation, some relation between that variable and temperature. And it could be a positively correlated variable. It could be a negative correlated variable. That once you document what that equation looks like in the modern world, you can go and measure that variable in ancient sediments and apply that equation and come up with a temperature estimate. Proxies are generally more useful to us if we know what mechanism drives that relationship, rather than just deriving some random equation. A classic example of this is oxygen isotopes. This is one of the major seminal paleothermometers that's been used for decades and decades and decades. And the idea behind it is that you have a few different flavors of oxygen that are part of waters and ice around the world. You have heavy oxygen, oxygen 18, and you have light oxygen, oxygen 16. Most of your oxygen is going to be oxygen 16. But as temperature changes, we find that there can be more or less transport of that heavy and light oxygen around the world. So if we know something about the reservoir conditions, we can figure out through a back calculation what temperature was if we measure that ratio. And in particular, there's that equation. And this is a very basic equation that doesn't have any of the variables filled in here. It's more just conceptual to show us that we found some correlated variable with temperature. The issue here is that we do need to make certain assumptions about the amount of ice, about the isotopic composition of the oceans around the world, about the isotopic composition of water vapor in the atmosphere and river water. For more recent past climates, these are not unreasonable assumptions to make, especially if the oceans and the ice sheets looked somewhat similar to how they do today. If we're going into deep time where we don't know as much about ocean reservoirs and ice caps, it may be a bit of a conceptual leap here, that we have a few assumptions that are unaccounted for. In contrast with that, these fluid inclusions are physical thermometers themselves. They operate using the same properties that make a glass bulb thermometer work, which is thermal expansion of a fluid inside of a vacuum. So in a typical bulb thermometer, like I show a cartoon of down here, if you heat it up, the fluid wants to expand. And so it grows, fills up the rest of the tube of the thermometer. If you cool it down, it wants to contract, it wants to shrink. And we've developed a measuring system, a bunch of markings on that tube that allow us to precisely measure what temperature something is at based on the height of that fluid. Now, the thermometers, the glass thermometers here work slightly different in the sense that they are always measuring temperature. The fluid inclusions we have, and and that we measure through a technique called microthermometry, they have a locked temperature, which is whatever the original temperature was when these things got trapped. It's the assumption that when they got trapped, they were trapped at the bottom of a lake or water basin, and there was no trapped air. It was just liquid. So I'm not sure how many people here are familiar with thermodynamics, but I'll try my best to explain this in a simple manner that everyone can understand here, which is that if we have a fluid inclusion and it formed at a set temperature, say 25 degrees C, if we cool it down, it's going to want to contract, but that fluid is trapped in a vacuum, so it can't. So it develops a negative pressure. It travels along this pathway, a suction, if you will, because it wants to shrink, but it can't. If you were to heat it back up, it would go back to the original conditions. Now, if we bring it into this gray field here, and we give it enough time, or we give it enough of an extreme pressure gradient, that suction can actually generate a little vapor bubble. And that vapor bubble acts as a cushion. So it allows the fluid to contract. And the vapor has no problem expanding and contracting at will. So it brings us back to a zero pressure. And as we heat it up, that air bubble will still continue to be there. And so it's always going to cushion it until it gets back to the original conditions when there was no air bubble. So if we are able to generate a bubble, we can measure the temperature at which the bubble disappears, and that gives us a good estimate of the formation temperature. Now, with these salt crystals, there has been a little bit of a discrepancy in the literature. Many years ago, my advisor and some students built up a laboratory experiment in which they grew salt crystals at a set temperature. And they grew them in two samples, one at 31.5 degrees, one at 41 degrees. And theoretically, if that method works, all of the measured temperatures that we get back from those fluid inclusions should match that. The problem is when they measured them and plotted up how many inclusions got different temperatures, most of the inclusions were nowhere near that. So you had many inclusions that would give you a temperature of -5 degrees, of 11 degrees, of 23, 24, 25 degrees. So clearly there's something wrong with the method. It's not working as much as well as it should. And they propose an idea here for why that is, which is that these salt crystals are not a super rigid mineral. You can break them with your fingernail. You can break them with a razor blade. Too much suction inside of those fluid inclusions can damage them. It can change the volume, and it throws that whole calculation, that whole thermodynamic curve we made on the previous slide out the window. The reason for that is that pathway in which it travels down or up when it's just liquid inside of the inclusion, if volume changes, if volume goes down, we jump to another path. And we jump to another path if we keep cooling it down and reducing the volume. If we expand the volume of the inclusion, it jumps down. And so if we were to follow these back to 0.0, it would actually yield a higher temperature if we overheated them. So the key thing here that we need to figure out for this to work is finding out how much of a change in temperature is permissible and how much creates a suction that damages the parent crystal. And a collaborator of ours, Emmanuel Guillerme, did quite a bit of analytical work using synthetic inclusions, using real fluid inclusions that grew at known temperature of various different brine chemistry. And they were able to figure out exactly how much pressure deforms fluid inclusions of different sizes. So that's useful to us. We can now figure out, based on our experimental setup, Are we destroying them or not? But the issue becomes when we try to not destroy them and we only try and cool them just a little bit, we never get fluid inclusions to nucleate little vapor bubbles inside of them. So we can avoid the risk of overcooling them or overheating them, but then we'll never be able to perform our analysis anyway, because we will never be able to generate those vapor bubbles. Now, a few papers out there on classical nucleation theory have said that given a sufficient amount of time, any metastable inclusion will nucleate a bubble spontaneously. The issue is sufficient amount of time for a geologist could be millions and billions of years, which I don't have that time to sit at a microscope. I looked up a few other papers that said if you try running sound waves through fluid inclusions that are slightly cooled, maybe you can generate vapor bubbles. And I set up a bunch of experiments in my office and in my lab using ultrasonic speakers to try and do exactly that. And while it may have worked, it was not super selective, not super useful. It still took a fair amount of time. And quite frankly, the setup made me look like a mad scientist. I had all these wires and all of these machines running in my lab. It turns out if you fire an ultra-fast laser pulse at a fluid inclusion that's just slightly below the temperature it needs to be, it nucleates a vapor bubble like that. It's perfect. And it doesn't destroy the inclusions because with this ultra-fast laser pulse, it's not imparting all that much energy. And it makes it so that we no longer have to sit at a microscope and hope some of them nucleate. We can go and point at a fluid inclusion and nucleate a vapor bubble. Now, a collaborator of ours who developed this method, Eve Kruger, tested this out in a bunch of other minerals, in stalactites, stalagmites, and found that it works for a lot of low temperature paleothermometry. We adapted the method with his help to work on halite fluid inclusions. So the idea here is you have an ultra-fast laser that through a series of mirrors and shutters and lenses is focused into the microscope and down on a sample. And I have a little trigger, a little button that I can press to zap it with a laser. So it's actually quite a lot of fun. You know, after you've been sitting in the lab going delirious, looking down a microscope for many hours, to have a laser button at your disposal. And when I say you're able to do it on demand, I really do mean that with the click of a button, you have a vapor bubble. So it's pretty sweet and it's easy to do. And when you do it selectively, you no longer need to cool it way past these thresholds for deformation. You no longer have to build up that crazy amount of suction to get these vapor bubbles to nucleate. So you don't risk damaging and you preserve the information. There are a few corrections we need to apply due to surface tension of the bubble itself, which are easy to calculate with if you have the thermodynamic relations here in the Young-Laplace equation. So we can account for it. There is also a correction term for if these grew at the bottom of, say, 100-meter deep lake. That lake water exerts a pressure on the fluid inclusions when they grow. So the temperature will be slightly different when it formed than when you measure it in the lab. So as long as we know something about the lake chemistry, which thanks to some of the previous research we do, and you know something about the lake depth, which again, thanks to the previous research project, we know a little bit about lake depth, we can constrain what these corrections should be. And they're not major. It's maybe about a degree or less for 100 meters of water. So I wanted to repeat that past experiment of growing inclusions at a set temperature and see if we experience the same problem. So I grew halite crystals in a water bath that was set at a very precise temperature that I measured independently at 25.05 degrees for about 3 to 6 months. And when I measured them, they pretty accurately and reliably reconstructed that temperature with pretty high precision at that. We wanted to test this out in a modern environment for which we also had an independently measured temperature record. And the Dead Sea offers exactly that. The Dead Sea is a very well understood basin with people that are constantly monitoring it and have been for decades. And we know about the sediments. We know when certain layers of salt grew, approximately what year. So we can pair up any fluid inclusion data with a historic temperature record. So we did exactly that for about 15 samples. Variance was generally very low. Water temperatures were very stable. And the temperatures we got out from the halite inclusions, which are the diamonds and blue squares here, do a pretty good job of matching the measured historical record of temperature. They capture, in many cases, within error, actual data points. And in other cases, they tend to capture annual trends that are observed in the historic record. So we know that in a modern environment, this works pretty well. The next test case we wanted to do was testing it out in an ancient environment, which we still have a pretty good understanding of. And in particular, that paper from over 20 years ago, 26 years ago, that my advisor wrote, they performed this thermometry on Death Valley fluid inclusions, Death Valley halites. And they observed these giant distributions of temperatures that they struggled to make sense of. So knowing what we know now, if we apply the new method, will we generate the same distribution here, or will we generate a much smaller temperature range? And with some new dates that have been applied to these sediments, we can constrain when these things formed. And we have 2 samples in particular that formed in the Holocene about 10,000 years ago, and towards the last glacial maximum-ish around 26,000 years ago. So we can compare them to known records of deglacial warming. So the old histograms are shown in gray. The new histograms using the updated laser method are shown in blue. So the temperatures are really pretty precise. And they give us some information about how much that deglacial warming was, about 4.4 degrees over those 16,000 years. So in an ancient environment, this method seems to work pretty well too. Now, Death Valley seems to be a safe basin to test it with because the sediments that we worked with were not buried super deep. They weren't heavily altered or anything. They were primary. They were original salt minerals. If I want to take that and connect it back to this Eocene record and develop a record of temperatures from the Eocene, how well do we think it's going to perform? So that's what this next project was. Going out and measuring a bunch of temperatures from different layers of this Eocene deposit and putting them in the context of deep time. So here we have age on the x-axis. And I also show for comparison what atmospheric CO2 was like. It was generally between 2 to 4 times what modern atmospheric CO2 is. So when you go out and read that atmospheric CO2 is 420 parts per million. In the Eocene, it was quite a bit more than that, maybe 800, maybe 1,200, maybe 600 parts per million. And these temperatures are hot. They're 25 to 30, 35 degrees Celsius. Putting that into context spatially, let's think about what temperatures are like in Wyoming and Colorado, where these basins are today. Now, why we can compare air temperatures with these lake temperatures stems from an important key piece of knowledge here, again, garnered by our friend and colleague, Dr. Olson, which is that in modern lake basins, if you have water depth above a certain threshold, say about 10 meters, 12 meters deep, the bottom water temperature starts to become very stable, and it starts to align pretty well with mean annual air temperature. So if you find one, you can make an estimate of the other. So let's do that for the Eocene temperatures and develop a record of continental air temperatures for the Eocene. This is what these data look like. It's very boring. It involves measuring hundreds of inclusion temperatures. What's important to note is that these temperatures have pretty slim histograms, which tell us that whatever the water temperature was, it was pretty stable. So it was likely a fairly deep lake basin, maybe above 10 meters deep in both cases, in Wyoming and Colorado. So these temperatures from individual halite samples, each one has 20 to 40 to maybe 70 fluid inclusions that have been measured per sample here, per data point. We have a bunch of temperatures and we have pretty good precision on them. However, we need to put that into context spatially for whatever latitude they are currently at and were at in the Eocene and whatever altitude they were at in the Eocene. So luckily, these temperatures match up pretty well with what other proxies have set. They fall on the higher side of things for 42, 43 degrees latitude, but they do still match up with an error of other proxies from the region. And if we compare it to known or well-estimated temperature gradients for the Eocene, they fit perfectly for sea level latitudinal gradient. So if we're going to try and compare that to modern temperatures, which sit at quite a bit higher elevation, currently Colorado and Wyoming are each, these basin floors lie at about 2,000 meters above sea level. That's quite a bit different from sea level. So we can compare the modern air temperature at these basins, 4.7 or 6.5 degrees in Colorado. But if we were to bring them down to sea level, they're a little bit higher at 10 and 13 degrees C. These temperatures are still way warmer than modern temperatures. In each case, about 10 to 13 degrees warmer at least, which does appear to be consistent for that worst case scenario climate model for what Eocene climate would have looked like and what 2150 will look like, assuming next to no action is taken. So it's our hope that these temperatures are now useful if we are developing new climate models and we want to test it against real data from the past to understand how good or bad these models are performing. We have that data. And as we collect more and more, we can fill in these gaps and better understand, A, what Earth's climate looks like so far back in the past, but B, we can understand a little bit more about climate dynamics in the Eocene, in the modern, and in the future. So with that, I'd like to thank you for your attention on this geology-heavy lecture and open it up to any questions if anyone has.
I was just curious why originally in like the first party project, you said that companies were interested in the data of like the past lake environment. Like I was just curious why they would be.
So that's a great question. These companies are mining that mineral trona, which is, they're not exactly interested in the ancient halites, but the halites occur with the trona. So they are interested in terms of knowing if they want to buy a lease for some plot of land that they're going to develop a mine for. They want to know how good that trona is, how thick the deposit is, and what the total volume that they're going to get if they start mining it. So they like to gather as much information, as much quantitative data as they can to understand that particular deposit. Now, why they'd be interested in also understanding the ancient conditions is so that they can develop a conceptual model for if they know what the conditions were like here and they mine it here, and it turns out that they get a lot of really economically viable minerals that they can produce and then sell and make money off of. Can we go to other basins where we know the conditions of the ancient environment, but we don't know how much trona is there, if at all? And can we make some sort of prediction? So it's building sort of an inverted model to find more of those economically important mineral deposits. Does that answer your question? Thank you.
This is like more on the broader side of a question, but like, what got you into this specific field yourself, like you personally?
So that's a great question. And it's one that when I get a little bit disillusioned by sitting in the lab for long hours, it's nice to remember that there is a broader world importance to this. So developing these data sets and developing these methods so that future scientists can use them and reconstruct past conditions, it's really, hard for me. It's really, inspiring to think that these methods will be important to the next generation of geoscientists who are trying to reconstruct ancient paleoclimates with great precision. It's also important to keep in mind that these data sets will be useful for people trying to understand future climate. We all care about the world in which we live, and we want to ensure that it's sustainable for generations to come. And developing these data sets is one way to do that. Now, the other shorter answer to that question is, getting to go out into the field, into Wyoming, and roll around in the dirt and get a lot of salt minerals is a lot of fun. It's fun to go climbing and hiking and getting your samples. So does that answer your question?
Yes, that's what I was looking for. Thank you.
Thank you.